Welcome to MSN Digit Max. I am Ram Lakshmi, Assistant Professor, Department of Mathematics, Madurai Sivahasi Nadars, Pioneer, Meenakshi Women's College. Here is a learning resource for Topology 1, 2MMA3C2, Unit 1, Module 2. In previous module, we covered the topics definition of topology and its examples, topological spaces. In this module, the topics covered are basis for a topology and its examples. Section 2.2 Basis for a topology. Definition: if capital X is a set, a basis for a topology on X is a collection script B of subsets of capital X. Script B is a collection of subsets of capital X called basis elements. Script B is a collection of subsets of capital X and the elements of script B is called basis elements, such that script B is set to a basis for a topology on X. It satisfies the following two conditions. First one, for each X belongs to capital X, there is at least one basis element B belongs to script B containing X. Second condition, if small x belongs to capital X, also it belongs to the intersection of two basis elements B1 and B2. Then there is a basis element B3 belongs to script B containing X, such that this B3 is a subset of B1 intersection B2. If script B satisfies these two conditions, then we say that script B is a basis for a topology on capital X. Next definition, if script B is a basis for a topology tau on X, the topology tau generated by script B is described as follows. A subset U of X is said to be open in X, that is to be an element of tau. We already seen in the definition of open set, tau is a collection of all subsets of X, and tau satisfies the topological conditions, then tau is said to be topology on X. Also we say that the elements of tau are open subsets of X. Here also we can say that an element belongs to X is said to be open in X, that is to be an element of tau, if for each X belongs to U, there exists a basis element B in script B, such that X belongs to the basis element which is subset of U. If we can write X belongs to B, where X belongs to capital X and B belongs to script B, and B is a subset of U, where U is the open subset of X, then we can say that tau is generated by script B. Next result, to verify that tau generated by script B is a topology on X. We have already know that the topological conditions, first one, empty set and the whole set X are in tau. Second condition, union of collection of subsets of X which is in tau is also in tau. Third condition, intersection of any subcollection of elements of tau is in tau. Proof: clearly empty set belongs to tau. Let X belongs to capital X. Since script B is a basis, by condition 1, there exists B belongs to script B such that X belongs to B subset of X. Hence we say that X belongs to tau. Condition 1, empty set that the whole set X are in tau, hence the condition 1 is satisfied. For condition 2, let collection U alpha be any subcollection of tau. Let capital U is equal to union alpha U alpha. We have to claim U belongs to tau, which means our union of finite collection of elements of tau. We have to claim U belongs to tau. Let X belongs to U, then X belongs to U alpha for some alpha, because we define U is equal to union alpha U alpha. Since U alpha belongs to tau, there exists a basis element B belongs to script B such that X belongs to B subset of U alpha and U alpha is a subset of U. From this relation, we can write X belongs to B subset of U. By the definition, the topology generated by the basis, we can write U belongs to tau, which means U is equal to union alpha, U alpha belongs to tau. Condition 2 satisfied. Union of any collection of elements of tau is in tau. Third condition, intersection of elements of tau is in tau. Let us verify the third condition. Let U1, U2, etc. Un be elements of tau. We have to claim U1 intersection U2 intersection etc. intersection Un belongs to tau. We shall prove this by induction on n. For n is equal to 2, we only take two sets U1 and U2 belongs to tau. Let U equal to U1 intersection U2. We have to prove intersection of elements of tau is in tau. Let X belongs to U. We define U is equal to U1 intersection U2. Hence, U belongs to U1 as well as X belongs to U2. Since U1 belongs to tau, there exists a basis element B1 such that X belongs to B1 subset of U1. Since U2 belongs to tau, there exists a basis element B2 such that X belongs to B2 subset of U2 by the definition of tau generated by script B. From these two relations, we can write X belongs to B1 intersection B2 subset of U1 intersection U2. Since script B is a basis, by condition 2, there exists a basis element B3 belongs to script B such that X belongs to B3 subset of B1 intersection B2 subset of U1 intersection U2. From this relation, we conclude that X belongs to B3 subset of U. By the definition of tau generated by script B, U belongs to tau, which means u is equal to u1 intersection u2. For only the two sets of intersection, condition 2 is true. Assume that the induction hypothesis for n minus 1 is true. That is u1 intersection u2 intersection etc. un minus 1 belongs to tau. Now we have to prove for n. We can write u1 intersection u2 intersection un minus 1 intersection un as intersection of u1 intersection u2 intersection un minus 1 and un. By induction hypothesis for n minus 1, u1 intersection u2 etc. un minus 1 belongs to tau. Also we define un belongs to tau. Therefore, u1 intersection u2 etc. un minus 1 intersection un belongs to tau. Condition 3 is verified for n. Hence, we say that finite intersection of elements of tau is in tau. Hence, the tau generated by script B satisfies the three topological conditions. Therefore, tau is a topology on X generated by script B. Next, example 1. Let script B be the collection of all circular regions. Consider interior of circles in the plane. Then script B satisfies both the conditions for a basis. Let us verify that two conditions. First one, if x belongs to x, there exists at least one basis element B belongs to script B such that x belongs to B. Second condition, for x belongs to x, there exists a basis element B1 and B2, and x belongs to B1 and intersection B2, there exists a basis element B3 such that x belongs to B3 and also B3 is a subset of B1 intersection B2. Proof: for each x in the plane, there is a basis, say circle, with the center at x contained in the plane. Hence, x belongs to any one of the circle, therefore condition 1 holds. Let B1 and B2 be two circular regions. Let x belongs to B1 intersection B2. We can find B3 from the diagram. We can see that we can find B3, a circle with the center at x contained in B1 intersection B2. Therefore, B3 is a basis element. For each point x belongs to B1 intersection B2, there exists B3 belongs to script B such that x belongs to B3 subset of B1 intersection B2. Therefore, condition 2 holds. Hence, we can say that script B, which is a collection of all circular regions in the plane, is a basis for plane. Next example. In previous example, we consider the circular regions, interior of circles in the plane. In this example, we consider the rectangular regions, interior of rectangles in the plane. Let script B be the collection of all rectangular regions, interior of rectangles in the plane, where the rectangles have sides parallel to the coordinate axis, which means the breadth is parallel to x-axis and the height is parallel to y-axis. Then script B satisfies both conditions for a basis. Let us verify that for each x belongs to capital X, we can find a rectangle containing x whose sides are parallel to the coordinate axis. Hence, condition 1 holds. Next, we have to prove let B1 comma B2 be two rectangular regions, then x belongs to B1 intersection B2, whereas there exists B3 belongs to the rectangular region such that x belongs to B3 subset of B1 intersection B2. For let x belongs to B1 intersection B2, we can find B3 a rectangular containing x contained in B1 intersection B2. Therefore, B3 is a basis element. Hence, we conclude that for each point x belongs to B1 intersection B2, there exists B3 belongs to script B such that x belongs to B1 and B3 subset of B1 intersection B2. Therefore, condition 2 holds. Hence, script B, the collection of all rectangular regions, interior of rectangles in the plane, is a basis on a plane. Next, example 3. If capital X is a set, the collection of all one-point subsets of X is a basis for the discrete topology. Already we defined the discrete topology, the collection of all possible subsets of X. Which means if we collect tau as a collection of all possible subsets of X, it must be a topology on X which is called discrete topology. For this discrete topology, we can define the basis, that means script B contains the collections of all one-point subsets of X. Next, lemma 2.1. Let capital X be a set. Let script B be a basis for a topology tau on X. Then tau equals the collection of all union of elements of script B. Since script B is a basis for the topology tau, the collection of elements of script B is also the elements of tau. We already see that script B is a collection of elements of X such that script B must satisfy the two conditions. Here, script B is a basis for the topology tau, or the collection of all elements of script B are also elements of tau. Since tau is a topology, their union is also in tau. Since tau is generated by script B, conversely, given u belongs to tau, for each x belongs to u, there exists an element bx belongs to script B such that x belongs to bx subset of u. From this relation, u is equal to union of x belongs to u bx, where u equals a union of elements of script B. Therefore, tau equals the collection of all union of script B. Next, lemma 2.2. Let script B and script B dash be basis for the topologies tau and tau dash respectively on X. Then the following are equivalent, which means script B is a basis for tau and script B dash is a basis for tau dash. We are going to prove the equivalent conditions that tau dash is finer than tau implies for each x belongs to capital X and each basis element B belongs to script B containing X, there exists a basis element B dash belongs to script B dash such that X belongs to B dash subset of B. First proof, 1 implies 2. We are given X belongs to capital X, B belongs to script B and X belongs to capital B, where B is a basis element of script B. Therefore, B belongs to tau. From 1, tau is a subset of tau dash implies B belongs to tau subset of tau dash. Since tau dash is generated by script B, there exists B dash belongs to script B dash such that by the definition we can write X belongs to B dash subset of B. Next, 2 implies 1. From this relation, we prove that 1 implies 2, which means we take tau dash is finer than tau and we prove X belongs to B dash subset of B. Next condition, 2 implies 1. Assume the hypothesis that for each X belongs to capital X and each basis element B belongs to script B containing X, there exists a basis element B dash belongs to script B dash such that X belongs to B subset of B dash subset of B. Assume the hypothesis. Let X belongs to U since script B generated by tau, there exists an element B belongs to script B such that X belongs to B subset of U. By condition 2, there exists B dash belongs to script B dash such that X belongs to B dash subset of B. From these two relations, X belongs to B subset of U, X belongs to B dash subset of B, we can write X belongs to B dash subset of U. Therefore, by the definition of the topology generated by tau, we can write U belongs to tau dash because U contains the basis element of tau dash. Hence, tau is a subset of tau dash, or we can say that tau dash is finer than tau. Next example, the collection script B of all circular regions in the plane generates the same topology as the collection script B dash of all rectangular regions. Here script B dash is a rectangular regions and B is a circular region, and we have to check the collection script B of all circular regions in the plane is same as the topology, the collection script B dash of all rectangular regions. It is clearly explained in the figure. Thank you.